first speaker, who is Anders Lø, who will tell us something about type-level web APIs with Servant. So, go ahead, Anders.
Thank you very much. So this is joint work with Alp, Sönke, and Julian. Sönke and Julian are actually both over there. And I should say in the beginning that they really deserve all the credit, I mean, all three of them, because they've come up with Servant. I've just recently become very interested in Servant, and I've asked too many questions and made too many suggestions, which somehow resulted in me standing here now. But yeah, it's really mostly their idea. So Servant is a Haskell type-level DSL for describing web APIs, and let's start with an example of how that looks like. So here is an example web API that you can write down using Servant. It's a Haskell type synonym definition. It describes an API that can respond to GET requests at the root path and is supposedly answering with some JSON encoded int to such requests. And it can also reply to requests under the step path if they have the post method, and then it doesn't give any particular response. And this is just a Haskell data type definition, and these things, and also this one and this one, they're the things that are provided to you by Servant. So if you look at an informal description of what the API does, you can think of it like this. So ideally, if you send a GET request to the root, you should obtain the current value of some counter, and if you send a POST request to step, you should increment the counter. Because it's a Haskell type, you have, well, it's more or less first class. It's as first class as types in Haskell are. So you have all the abstraction mechanisms available that the Haskell language gives you on the type level. So for example, you can rewrite the same API just by introducing yet another type synonym definition just for the GET part and one for the step part, and then combining the GET part and the step part together. You can also do things like say, oh, well, integers have all sorts of different purposes. I want to make it explicit that this thing, the integer that I'm returning here, is a counter. So you define a new type in this case in Haskell, a type that is isomorphic to an integer with a constructor and a destructor, and derive some bunch of type classes for it, and then you can still use it more or less in the same way as before. So this is an API description in Haskell. What can you do once you have such an API type? And in fact, Servant's answer to that is that it doesn't tell you exactly what you can do with it, but it offers you quite a few things, and you can define more things if you like. So things that you can do out of the box with Servant is you can generate documentation for a given API specification. You can implement a server that implements that API. You can obtain a client that talks to some other server that implements the API. And you can also describe type-safe hyperlinks within the API. So I'll go through a couple of examples of these on the next few slides. So documentation generation. If you want to use the API that you've just seen in order to obtain some documentation, then you first need some way to link the type level and the value level somehow. So if you want to call a function to generate the documentation on something, and you want to say, okay, I actually want this API that is the counter corresponding to the counter type, you somehow need to link the value and the type level, and you can use a so-called proxy for that. The proxy does have no computational content, it's just a value, but it's tagged with the type that we are interested in this case counter, and then we can use it in something like this. We can say counter docs is just a string, that's the documentation, and it's the result of applying the docs function, which is provided by Servant, to the counter API proxy. That gives you some abstract syntax tree of the documentation, and then you can transform that abstract syntax tree to Markdown, for example, using the Markdown function. And the markdown function is unremarkable in that it is just a translation, but the docs function is one of several interpretations of this type level DSL that Servant offers. And these interpretation functions, they all have similar types. They all work on a proxy. They sometimes take some additional information. They always have a class constraint on the API type that says, okay, if you're within the Servant language and possibly fulfill some additional constraints, then we can generate these docs, and then ultimately it produces a result. So in this case, if you try this, that actually fails at compile time because we still lack necessary information in order to generate documentation. And in particular, what Servant requires you to do is if you have an API that has inputs and outputs, it needs to know how to compute sample input and output values so that it can use them in the documentation. So in our case, we need to make counterval an instance of toSample and just say, oh, this is a potential value of the counterval type, but you could give a slightly different definition there. And then if you run this and you render the markdown, and I'm only showing the part for the get route here, you get some documentation like this. And this is still very raw. You can obviously imagine that you want to have actual meaningful explanation here what this particular request is supposed to do, and obviously the Servant package offers this additional functionality to attach extra information here, but this kind of raw documentation you get without any further work. Okay, so let's look at probably the most interesting interpretation that Servant offers, that is to interpret an API as a server. So if we just look at the type, then what can we reasonably expect the code to do for free for us? And so if you think about it, one thing that we can expect is that the server can decide if there is an incoming request to the server, is that request actually valid or not? And it should also sort of dispatch the request to the right handler. So we should have some kind of component-wise way to specify handlers, and the server should automatically do the routing from the request to the right handler. But we obviously still have to provide ourselves the information about what we really want to do with the inputs, how we want to turn inputs into outputs. So this is something that cannot be done for free. So how does that work in practice? If we look at the API again, and if we just focus in on the first part for the time being, on the get counter part, then the handler for that part should be something that produces a value of type counterval. And in practice, this is handled by a type level function in Servant. The type level function is called server, and that takes a type such as the get counter type and expands it. So this is GHC's notation for type level equality to something like this, which essentially just says it's a counterval. But on the way to produce a counterval, you can also do I/O, and you can also throw an error, a Servant-specific error. But if we don't want to use that functionality, we can just assume that we want to produce a counterval. And indeed, one possible implementation that we can use is to just assume that we have some globally given variable which contains the state of the current counter. I'm using a transactional variable here, which in Haskell has the advantage that it is automatically thread safe. So, and then I'm reading the value from that counter variable and returning it. And that is the handler for the get counter function. Now for the step counter, here I need to produce something of unit type in the end. And actually the fact that there is a path specification here doesn't contribute to the type of the handler at all. So that's just dropped. So here we just have to increment the counter by 1 and do the same as before. And then finally, if we want to put two things together, well, the handler for such a specification should just be a combination of two handlers for the individual parts. And that's indeed what Servant does. Servant follows the questionable Haskell tradition of using the same kind of similar-looking notation for all sorts of related concepts. So this thing here exists both on the type and on the value level, and it's just a different notation for pairs, really. So you can think of it. This is a pair of the server for a counter, is a pair of a server for get counter and a server for step counter. And also the handler is just a pair of the handler for get counter and the handler for step counter. And then if we want to run this, we call a function serve, which looks just like docs in the sense that we take a proxy again, we have a class constraint on it. We additionally take the server of the API, that's the handler, and then we form something that is an application, and the application can then be run on a particular port like this. So if we want to actually run this thing, we initialize our transactional variable to 0 in the beginning, and then we run it, and then we serve that API. So, and if we do this, then it statically checks that we have handlers for all our components in the API, and also statically checks that all the types of the handlers are okay. And conversely, when writing the handlers, we don't have to worry about anything of the incoming types. We don't have to do any type checking anymore. We can just assume that the incoming values have the right types, and we can produce values of the right output types. So this is all good. So I've put everything that is needed for just the server interpretation on one slide again, and I've not particularly optimized for number of lines. So if you look, what you need is the API, and if you really want to cut it down here, you can probably cut it down to something like 3 lines plus the proxy. Then you need the handlers. If you want to, you can probably cut this down to 1 line, and you don't even need the type annotations. And then you need the little driver. So it's all in all very concise, but you have the type clearly separated from the implementation. A third way to look at an API is to interpret it as a client. So what we also have available in Servant is a function client, which again looks much the same as the function docs or the function serve. And it again takes a proxy, has a class constraint on it, and it takes some additional information. In this case, it's the base URL, and produces something of type client, and client is another type level function. And we can use it like this. We can call client on the counter API and tell it to run on localhost on a particular port. And then we get, in this case, a pair of handlers, because the API was a pair of endpoints. So we can match on the get counter and on the step counter functions that we get out, and then we can use them at these types. So get counter is again something that can, in I/O and potentially throw a particular arrow, produce a counter val, and step counter produces a unit in the end. And we can use that in a program or interactively on GHCI, just like this. So we can, if we have a server running somewhere on localhost, we can use get counter to get the initial value back, and then we can step it once, and we can get it once, and we get 1 back. And 2 remarks about this, perhaps. So first of all, if you look at the get counter and the step counter as they're used here, there's really not much difference between the types that you have for the handlers on the server side themselves and for the types that you have for the querying functions on the client side. So you can more or less write the same code on both sides. And also, while it's obviously quite useful to use Servant both as a server and a client generator, for example, to test your own server if you're working with Servant, this client interpretation is also useful for existing APIs that have been written by completely other people. You just give a Servant specification of an existing API, and you can very quickly get a client that works with it. Okay, so one more thing is if you modify the API, so if we assume that we are adding a third option, in this case, I'm adding a set counter method that requires or works like as a response to put requests on the root path, but requires a request body which contains a JSON encoded counter, and then we add set counter to the counter API. And if we do something like that, then immediately the server and the client that we've just defined become type incorrect, which is a good thing, right? I mean, we have changed the type of our server or of our client, of our API type, and now the interpretations that we've already worked with that have type-specific additional information, they are no longer matching up, and this is immediately caught. But adapting, for example, the server is very straightforward. In this case, the handler type corresponding to set counter is a function that gets a counter val as an input and produces a unit type as an output. And it just writes the new value that it gets to the T-var, ignoring the old value that might have been there. And then the overall handler for everything is now a choice between 3 different handlers. Okay, so let's look at what servant really is at this stage. So it is this type level DSL that we have seen, and it also gives you a number of interpretations out of the box. So it gives you this documentation generation, the server, the client interpretation, the links, and 1 or 2 minor things more that I'm not showing here. But there is another aspect that is very important in the design of servant, and that is that it is extensible. So, and it is extensible in the expression problem sense. It is extensible with respect to the DSL constructs itself. So the type level DSL provided by the servant isn't closed. You can add your own new constructs to it. And it's also extensible with respect to the interpretations. So there is also no fixed set of interpretations available. You can define your own. And that's an important aspect of the design of servant, and is very good because it means that if servant doesn't currently do everything that you want, there is a high chance that you can still do what you want without requiring us or anybody else to change the library. Right? Okay, let's briefly look at this type level DSL. So what's a web API in general? A web API is describing something that reacts to requests and gives according responses. And the requests that are accepted can be constrained by the API in various ways, according to the path that they are using, according to parameters, query parameters that they can be using, that certain HTTP headers should be present, that a certain body should be present of a certain shape, or that a particular request method, such as get, put, post, should be used. And responses can also be constrained in various ways, in what kind of status code they should be sending, and what kind of headers are included in the response, or what shape the body of the response has. And this inspires the base design of the API language. So the core API language looks like this. You have either a choice between 2 sub-APIs, or you have this nesting where you have an item that somehow constrains the incoming requests and then constrains everything that comes underneath. Or you have a method which is a get, put, post thing. So the items, to show just a few examples, they can be things like symbols. Symbols are just type level strings that restrict the path of the requests. They can require particular headers. You can require a particular request body. You can capture a particular dynamic part of the input, or you can match on query flags or query parameters in various different ways. And for the query flags or parameters, the symbols here, they denote the name of the query parameter. For the capture thing, the symbol being used here, the string being is mainly being used for documentation purposes. And then the methods, they can be get, put, post, delete, patch, and then there is an escape mechanism raw where you can sort of dispatch to the underlying web framework that you're happening to use. So by default, Servant is using Warp and WAI, which are existing packages for Haskell, but it's not tied to them in any strong sense. So you could build Servant on top of Snap or Hapstack or Yesort or Spock or Scotty or whatever. The methods then have a parameterization by a type level list of content types. Okay, so if we map this API to Haskell data types, I'm only showing a few of them here. It looks more or less like this. So you, rather than what you might think if you're familiar with the latest Haskell type system extensions, we're not actually introducing a kind called API, which has data types associated with it that correspond to these three options, but we just have data types for each of the individual constructs. And the reason is, again, extensibility. So if we would introduce our own kind in Haskell, at the moment, user-defined kinds are always closed. But by creating one data type for every construct, we have slightly less precise kinds on the Haskell level than we would like, but we are at least extensible, and we can easily define our new language constructs. Okay, but otherwise it's very systematic. And then how are interpretations defined? Each interpretation, as we've already seen from the types of the functions, is essentially specified by a class. So for example, the HasServer class provides a type function which computes the server of an API as the type of the handler for that API. And it also gives you a root function which has a very similar type to the serve function. And in fact, the serve function that we have already seen on the slides is just a relatively shallow wrapper around this root function in the end. And then how do you now define instances for this class? So in principle, you follow the grammar. But the grammar, if you remember, has different syntactic categories. So we have an API, and then we have items, and we have methods. And so one option would be to actually have not one class, but three different classes and give a different instance declaration for all three of them and have them interact. But again, this sort of leads to hard to manage Haskell code because you get a lot of overlapping instances in rather tricky ways. You can often work around them, but actually it turns out to be much easier, even though again it's perhaps slightly less obvious that way, to sort of inline as much as possible into the API category and transform the grammar so that it is essentially just based on this API construct and that all the individual items are inlined here. So you have now many cases with this nesting constructor, one for each item, and also inline all the methods in here. And then you're essentially just having to deal with two categories, two major categories, the API category and the content types category. And then you can define just instances for each of these different cases that you have seen on the previous slide for the HasServer class. And then for content type handling, you have a number of other classes that are involved. So intuitively, the idea here is if you have a GET request that looks like this, then it says, okay, on a GET request, I respond with a value of type myType, and I can deliver it according to three different encoding methods. So I can deliver it as a JSON encoded value, as an HTML encoded value, or as a plain text value. And each of these are different options, and a client can select using an accept header that it wants to have a specific encoding, And if it doesn't select one, then by default, the first one is being used. And so there is a class accept that is instantiated by every such content type descriptor, JSON, HTML, and plain text, that actually associates a media type with this descriptor. And then there are two classes, MIME render and MIME unrender, that handle the actual conversion from a byte string to a Haskell value of a particular type, or the other way around. And they're relatively flexible, but I won't go into the details here. Okay, type-level computation and servant is everywhere. So in particular, we have the server interpretation that we've already seen, computing the types of the handlers that are involved. Similarly, I've not made that as precise, but the client interpretation obviously also computes the types of the request functions that it generates from the API. The link interpretation that I haven't really talked about much is essentially taking two API specifications and computes whether one API fragment is contained in another, and then if it does, as evidence, it produces the path. And the documentation interpretation also uses something like the link interpretation in order to give you a mechanism to attach specific additional documentation, such as the what a method does or what a particular part of the API is for to certain parts of the API. So here, as a small example, is how the handler type function instances look like for the server interpretation. So we can indeed see that the handler type for a pair of API components is a pair of handlers, and that if you have a path, that it is just ignored, and that if you have an input parameter like a request body, that it just turns into a function parameter of the handler. How can you extend the language? Well, if you add a new interpretation, you just define a new class and then provide instances for all the syntactic constructs that you want to interpret, either all of them or just the ones that you're interested in. And if you add a new language construct, you just define a new data type and provide instances for all the interpretations that you're interested in. So it's really very straightforward to extend it. There's lots of stuff that I haven't talked about, some of which a little bit is mentioned in the paper, even more is mentioned on the website. There is an efficient routing implementation that is going to be in the next release. We are going to hopefully improve the type error messages that you're going to get. We are also going to improve the error handling a little bit, like produce more systematic and more controllable error status codes. There has been a lot of ongoing work on authentication. That will be a new combinator added to the type level DSL. There is a new CSV content type. There is also a JavaScript client function generator that is already in Servant now. I think Alp has recently implemented a mock server generation interpretation that actually gives you a server completely for free without even defining any handlers, by just taking random inputs and taking them to random outputs, essentially. There is ongoing work on providing documentation and stuff in more advanced formats, such as Swagger or other API description languages. As a final point, I want to say how this all relates to generic programming. So if you look at data type generic programming, the aim is to describe many or all data types systematically using some kind of DSL. And you often use structural combinators on the type level to describe the syntax of data types. And in Haskell, you have mostly sums and products that are important constructs there. And then generic functions interpret that structure and work for many data types and are robust to change and save you boilerplate code. And this is really very similar. This is very inspired by it. Only the aim is not to describe many or all data types of our Haskell language, but it's very specifically to describe a particular domain, like in this case, web APIs, but it could be a different one. So you're describing the syntax of a particular domain on the type level, but then you use structural combinators, or you have something like sums, which is this one, you have something like products, which is this one, and then you have your generic functions, which are our interpretations, and they have the same kind of advantages. They work for all the inhabitants of the domain, and they are robust to change. You get everything checked, and you get all the boilerplate and for free. So you could apply this idea equally to other settings, like, for example, database schemas or configuration options for a program, or just general context-free grammars and define parsers and printers and transformations and stuff like that. So what is the conclusion? By putting as much as possible information into the type system, we save a lot of boilerplate code, but we are also much more robust and concise, and servant servers and servant clients are very easy to refactor because you have all this additional help by the type system, and you don't have to write a lot of stuff that is obvious. And Haskell is actually a good fit with all its current extensions. So I don't find it particularly beautiful, I must admit myself. I mean, type level Haskell is cool, but it's not exactly beautiful, but still it's quite up to the task, and it's the essential features that we need are type classes, type families, and data kinds, type level strings, and kind polymorphism, this sort of stuff. But type classes are extremely essential because we need this extensibility. And this is something many dependently typed languages give us more power on the type system, but have less in terms of extensibility to offer. And this domain-specific generic programming technique can hopefully be applied to other domains as well. So if you want to try it, this is the web page. There is tutorials, explanations, packages to download, lots of further information. Also links to the paper, links to other talks and presentations. And Julian and Sönke are also going to offer a ICFP tutorial on Friday afternoon. And perhaps you can still do a late registration if you haven't made one yet. Okay, thank you.
Okay, so the format of WGP is that the speaker has a 30-minute presentation slot, and we have some a discussant who will talk about the paper and give his opinion on that. Okay, I think before we go to discuss it, if you have any questions on this, we can ask them now as well. I actually have a question. So if you go to your conclusion slide, you said, oh, this is such a great idea because we put so much into type safety. We didn't put very much into kind safety, right? Because you're just, everything is kind star. And is it actually possible to write malformed or illegal APIs?
Yes, obviously. I mean, because a lot of this stuff is kind star. Yeah. But that's a pragmatic choice. I mean, I don't think it's very difficult once you get used to, because the type level DSL is relatively small and it's relatively confined. So you're, I don't have observed me making strange mistakes on that level very often, whereas I make type errors all the time, I must admit. But I agree, it's sort of something which I dislike. There is a well-known trick how you can sort of have user-defined open kinds in Haskell encoded, but it's an encoding, and I don't think it's a good trade-off in our case. So if there was a way to define new kinds that are also open, I would immediately use it. That would be nice.
So one thing when I saw you were kind of the type level trickery you were up to is, one thing I was expecting you maybe to do is, instead of having all these type synonyms to assemble APIs, and then kind of use a proxy to reify them. One thing you could have done is work with singletons from the onset, and then use that to assemble these APIs. Is that something you considered?
It's an interesting idea. I don't think I've actually tried that personally in the servant setting, but I've tried something very similar in a different setting just last week, and there I had the problem that if I do that, I still am at a point in Haskell where I actually have to specify the type explicitly due to like lack of inference and something. And then you basically don't end up winning much if you sort of write down your nice little construction using singletons, which expands to having a 50-line type, and then in addition to giving the singleton specification, you're also required to write this 50-line type signature down. But I'm not saying that this necessarily applies here, but it's something to watch out for. Otherwise, it's certainly an interesting idea. Perhaps we should give the discussant a chance.
Let's give the floor to Atsu first, and then we can maybe slightly bad form on my part, because I only get to ask questions, and then otherwise you guys didn't get to ask your questions, but please save them.
all my questions.
Please save your questions.
Give you the microphone. Oh, I'm gonna, okay, yeah.
And then Atsu will share his thoughts on the paper.
Yes. All right, so what I really like about this paper is that it used all this type-level machinery to solve a real-life problem, namely the problem of REST APIs, which is something that is totally untyped usually, but this basically reinforces this with a type system thing. And so I really like the way the paper describes how all this type-level trickery can be used. What is nibbling at me a bit, but this is not your fault, but it's more of a thing that is going on here, is that you basically, part of the paper is also about steering such that you do not end up in the tar pit of type nastiness, right? And I think in the end this works beautifully, but if you just go, you go, oh no, we're in the tar pit of nastiness now. Yeah. What I'm also really interested in is, in the paper, it says that the motivation for actually doing this was that there was a problem at a company, and that this solves it. So I would like to know what the problem was and how this solves it, or what the experiences with this are. Who am I looking at? Oh, you. Sure. So did you have trouble with this before at this company, or is this more? This would be nice to have. Yeah. Okay. All right. All right. So is it still used in production at the Valora, or you're not working at Valora anymore? No, I'm working there. Oh, you are working there.
Yeah. In the motivating project, I think we have like 3 endpoints.
Oh.
It doesn't provide that much practical use.
So, and why is that?
Well, it's just 3 endpoints, right?
Oh, okay. So you, you went into the classic Turing pit mistake, right? Or mistake. It's also a way to be productive. Say, I have this problem with 3 instances. Let's make a very general solution for this.
Well, it was also that I was talking to Elle, and she was really interested in this. And then, yeah, I mean, this was just the motivating example. Maybe also only the motivating example for me. Elle was motivated by lots of other stuff.
Okay, right.
But there are other users that we are aware of, right?
Yep.
So I have officially worked with Laura, and I work with Live in Democracy,
Mm.
and we have been using it for very early days. There are other people who are connectors, so I mean, I've been using it in production. It does, the mechanism does solve, yeah, it does solve the very classic problem. I mean, so
Mm.
the
Yes, definitely.
possibly worse than that kind of confusion at all. And so there are all these sort of weird problems that client libraries don't get out of date, definitions get out of date, and all these things are sort of constant concerns in the context of programming, and seem to be, I would like to think, completely solved.
Oh, it's also nice that, so this type safety, it also provides you documentation safety, right?
Yeah.
In this case, it gave...
Would you like to say anything else on this, or should we open the floor to further questions?
Yeah, and one more question about the, so I think it's a bit of a double-edged sword, this type of programming in Haskell. And you also hint at this at the end of the paper, saying we want to do sublinear routing, which you now say you've solved. So was this a painful issue or not at all?
No.
So I thought, but I might be incorrect, that because this can be a sort of more complicated thing, that it might be hard to get right on the type level.
Oh yeah, but you don't actually have to do everything in the interpretations
Sure.
on the type level.
Uh-huh.
So, in principle, the only thing that you need to stay on the type level for is things that affects the types of other
Yes.
components that are involved. Like in the server interpretation, you want to stay on the type level as long as you have sort of squeezed in the handlers into the right points. But afterwards, you can in principle turn to a normal untyped representation to everything that you do otherwise, or less typed, untyped as
Yes,
well. but less
yes.
typed.
Well, you or
So
just a,
there's no real limit to the kind of things that you can do just by using this general approach.
yes. As soon as you don't need the type, it on the type level anymore, you just throw it down to the data level and then or value level.
It's not very difficult to do the more efficient routing. It was just, I think, a normal approach. Like if you have this idea to represent the APIs this way, then first you're trying to do everything as directly as possible in order to make sure that this actually works, and then you're trying to gradually improve the efficiency and stuff. So yeah, this is the phase we were at now.
Yeah.
Okay, let's open the floor to more questions. We just have someone raise their hands.
So you talked about documentation, safety, and sort of that documentation should be kept up to date. And you also talked about that it was possible to add extra bits. Does Servant sort of ensure that when you add extra bits and then you decide that now step should no longer be called step, it should be called increment or something like that, that the sort of extra attachment that they don't sort of fall off or dangle on some other old part of the API?
Yeah, so this is a good question. So I think we should have done this before. I'll repeat the question. So, so the question is, does Servant take any effort to ensure that if you are renaming things or otherwise evolving your API, that your additional bits in the documentation are kept up to date? So there's always a distinction we have to make between what the current software does and what you could in principle do. And also there is an aspect of how much effort you're willing to take. So if we take a simple example and you're having a textual description of a particular endpoint and you're naming, say, part of the path in the textual description, then normally there would be no link between the string fragment that you're using and the path in your API. And currently there is also nothing provided by the Servant docs package to do this, as far as I'm aware of. But it would be possible to add such a feature where you sort of have a way to insert aspects from the API into your strings at particular points and have that checked. The thing that is being done right now is that if you have an API and you're saying, for example, the API is structured that I have this big blob and then I have that big blob, and I want to add an additional piece of text on the top of this first big blob, that you're sort of attaching it to actually the structural piece of the API. And if you're changing the position or if you're removing it completely or stuff like that, then you will get a type error because it's no longer there. And it's checked that you're sort of That's what I meant when I said it uses a similar mechanism as the type safe links one. So if you're identifying a subpart of the API and you're saying I want to put my extra documentation there, then it is actually statically checked that that you're pointing to an existing part of the API that has the right types. Yeah.
Okay, maybe a bit of a trivial question, but this whole rookie lobby, right, at the beginning you said it's basically a pair, but when talking about generic consensus, you said it works as a sum, not a product.
Yes, so, okay. That's not an uncommon thing. So if you think about sum types in general, so they're giving you a choice of different things. And then if you're thinking about eliminating sums, which is essentially case statements, how do you eliminate a sum? By providing a case for every possible choice of that sum. And it's exactly the same situation that we have here. So we have an API that essentially gives you a choice between two different things, but now if we are talking about servers, we're wanting to handle all possible choices you can make, so we have to give produce a product of handlers. I mean, that's a normal relation between sums and products that exists in many places.
Yep. One last question?
You talked briefly about fragments where you can sort of take parts out. So is it possible, and then is it convenient to have an API where you, for instance, can choose between a number of lists, and within each list you can choose a sort of a specific element? So you basically have two fragments, one saying the list identifier, and then a slash and then the element identifier. Could you describe such a path? You
mean whether I could generically describe such a path for all possible situations?
Thinking that I know a number of APIs where there is sort of this, they have this structure where you sort of select a collection and then select the element within that collection. And in the API, you would normally have sort of saying this fragment, here you give a collection identifier and then you give an element.
Right. I mean, there's certainly an option to use something like a combined type synonym, the parameterized type synonym, say, and a handler transformer or something like that to capture recurring patterns within your API. So if you have a situation like this one where you have many different resources that are all accessed by sort of the same structure of sub-APIs, you can certainly abstract that out within Servon using normal abstraction mechanisms that are provided by Haskell and parameterizer. I'm not sure whether that answers your question.
I think it does.
Yeah, okay.
Okay, let's thank Anders one last time. And
Okay.